Today we are solving LeetCode 1351, count negative numbers in a sorted matrix. This is an easy problem, but it teaches a very important DSA idea. When data is sorted, do not blindly check everything. Use the sorted structure to skip unnecessary work. Here the matrix is sorted both row-wise and column-wise. So we will first think from brute force, then improve it and finally reach the optimal O m plus n solution. So let's read the problem carefully. We are given an M cross N matrix called grid. The important condition is each row is sorted in non-increasing order. Each column is also sorted in non-increasing order. Non-increasing means the values either decrease or stay the same. For example, let's say 4, 3, 2, -1, -2, -2. So this is a non-increasing sequence. This is non-increasing because numbers are going down. Our task is simple. Return the total number of negative numbers in the matrix. Negative means strictly less than 0. So -1, -2, -3 are negative, but 0 is not negative. Now let's look at example 1. This is our grid. If we count manually, first row has 1 negative, second row has 1 negative, third row has 2 negatives, and fourth row has 4 negatives. So it becomes total 4 plus 2 plus 1 plus 1, that is 8. So output is 8. Now let's consider one more example. Now it does not have any negative number, so output is 0 this time. Now whenever we solve a DSA problem, we should first think of the simplest solution. The simplest solution is go to every cell of the matrix. Check if the number is less than 0. If yes, increase the count. This will definitely work. Let's write its pseudocode. So first, we initialize count equal to 0. Then for every row, we check if the value is less than 0, then we increase the count. And finally, when the loop executes completely, we return the count. Now if there are m rows and n columns, we are checking every element. So time complexity for this pseudocode, that is order of m star n, because there are total m into n values. And the space complexity is constant order 1, because as we increase numbers in a row or in column, it does not increase. It remains fixed. We only use one count variable. Nothing else, only one count variable is being used. So space complexity is fixed. It does not increase with the number of elements in our matrix. Now can we do it better? If we look at the problem, there is the constraints. It says m comma n is between 1 to 100, and the values in grid I and j can be between 100 to -100. So maybe the solution can work, but the follow-up is, could you find an order n plus m solution? So this is not sufficient. So let's use the most important clue in the problem. The rows are sorted in non-increasing order and also columns are sorted in non-increasing order. This means larger numbers are towards the top left side and smaller numbers are towards the bottom right side. The negative numbers will appear towards the right and bottom side of the matrix. Now we need a smart way to count them without checking every element. So let's focus on one row. Suppose the row is 1, 1 minus 1 and 2. The row number in this numbering 0, 1, 2, 3, the row number 2, or the second last row 1, comma 1, comma minus 1, comma minus 2. Once we find minus 1, everything to its right will also be negative because the row is sorted in decreasing order. So if we stand at index 2 and the value is negative, then all elements from index 2 to the end are negative. This means we can count them together instead of checking one by one. Now the question is, where should we start? A very smart position is the bottom left corner. Why bottom left? At bottom left we can make a clear decision. If the current value is negative, then all the elements to the right of the row are also negative. So we can count them and move one row up. If the current value is non-negative, then the values above it in the same column will also be greater or equal. So they will also be non-negative. So there is no point going up. We should move right to find smaller values. So the movement is like this staircase movement. If the grid row column is less than 0, count all elements to the right and move up. Else, move right. This is like a staircase movement. Each step either moves up or moves right. So maximum number of movements will be m plus n, and this gives us the optimal time complexity. Now let's write the algorithm clearly. First take m equal to number of rows and n equal to number of columns. Start from bottom left. So row equal to m minus 1, col equal to 0 and count equal to 0. Now run a loop while row is greater than equal to 0 and column is less than n. Now at every position, if grid row call is negative, then we increase the count by n minus column, and then we decrease the row number. Why n minus col? Because from the current column to the last column, all numbers are negative. Otherwise, if the number is non-negative, col plus equal to 1. So we do, and finally we return count after running the loop. Now let's compute the complexity. At every step, either we move one row up or move one column right. The row pointer can move up at most m times. The column pointer can move right at most n times. So total time complexity is order of m plus n. So time complexity this time will be, and the space complexity remains the same. because we just use one variable, and our the number of variables that we use does not increase with the number of elements in the matrix. So space complexity will be of order 1. Just few variables, row, call, and count. These three we are using. This satisfies the follow-up requirement. Now let's write the code. So let m equal to length of grid and n equal to length of the so m equal to length of the len grid. So it gives us the number of rows in the grid, and n gives us the number of column in the grid. Then we initialize row, call, and count. So row equal to m minus 1, that is the last row, the bottommost row, and call equal to 0, that is the first column, and count equal to 0. Now we start running the loop. So while row is the either the starting row or the rows in between, starting and ending, or and the column is less than the last column. We check the condition. If the value at that row and call is less than 0, then we increase count by n minus call and decrease the row pointer. Else we increase the column, we increase the call pointer, and finally we return the count. So let's quickly understand this code. M is the number of rows, n is the number of columns. We start from row equal to m minus 1, call equal to 0. This means bottom left corner. If the current value is negative, then all the values to the right are also negative. So we add n minus call. Then we move up, row minus equal to 1. If the current value is non-negative, we move right, call plus equal to 1. Finally, we return the answer. Now let's dry run this example. So let's dry run. So here m equal to 4, n equal to 4, row equal to 3, call equal to 0, and count equal to 0. We started bottom left. So current value bottom left is grid 30, and that is equal to minus 1. Since row is sorted, all values from 0 to column 3 in this row are negative. So add n minus call equal to, so we add n minus call, and now this n minus call is equal to 4, and thus our count becomes 4. Now row equal to 2 and call equal to 0. Now our next value is grid 2 comma 0, that is 1. This is positive. So we, um, we move right, and by moving right we update the values. Row equal to 2, call equal to 1, count remains the same, equal to 4. Now our next value is, that is again equal to 1, grid 2 comma 1 equal to 1. So again that is non-negative, so again we move right. So row equal to 2, call equal to 2, count equal to 4. That remains the same. Now we check the next value, grid 2 comma 2, that is negative now. So we will compute what is our n minus call. N minus call equal to 2. This m and n are the length of the matrix. M is the number of rows and n is the number of columns. N was equal to 4 and therefore n minus call is 2. Now our count will increase. Count will become equal to 4 plus 2, that is 6. Then our row will decrease and call will remain the same. Row equal to 1 and call equal to 2. So next value is grid 1 comma 2, and that is positive. So we move right. That means row equal to 1, call equal to 3, count remains the same, equal to 6. Now next value grid 1 comma 3 is negative. So we need to compute n minus call. N minus call equal to 1, and therefore our count becomes 7. And then we give the row as the same row, and we decrease the row by 1. So row equal to 0, and call remains the same. Now next value is 0 comma 3. So that is again negative. So we compute n minus call once again, and that is equal to 1 again. Count becomes 8 this time, and row equal to. Now we need to decrease the row, and it becomes minus 1. So now the loop will end. Call remains the same because row is less than 0. So loop will stop now. So our final answer is the value of the count, and the count value is 1. So answer equal to output is 8, and this matches the expected output, right? Now let's take test example 2 also. So we again start from bottom left, and we have row equal to, let's write our m and n values. M equal to 2, n equal to 2. Row will be 1, and call will be 0, and count will be 0. So row is the bottommost row and call is the leftmost column. So we start bottom left. The value of grid 1 0 is equal to 1. That is positive. So we that is non-negative. So we move right. So we update call by 1. Call becomes 1. Row remains the same, and count remains the same. Now next value is grid 1 comma 1, and that is equal to 0. So that is again non-negative. So we increase the call by 1. Call equal to, row remains the same, and count remains the same. Now as we can see that call has increased the highest value. Call is equal to the highest value, that is call is equal to n. So we need to stop. So and our output is equal to the count, and count, the value of count is equal to 0. So output equal to 0, and that is correct. As you can see, output is 0. So let us test the code. Okay, the test case is passed. Now before submitting, let's quickly think about edge cases. Case 1 is all numbers are positive or 0. So answer should be 0. And second case is all numbers are negative. So the algorithm, let's say this is our grid. So in this all the numbers are negative. So the algorithm will start from the bottom left, and at once the count will become uh, call is 0 and my n is 2. So count will become 2, and after that it moves up and counts full row again. So answer will be 4 in this case. Now in case of single row, answer should be, for example, this is our grid. Here output equal to 4. Now grid equal to this. Here output should be 2, and that will happen because we will start with 4. Then it is then move right because it is non-negative. Then again move right, and because it is negative, then we do call minus call and minus call, and that is 2. So output will be 2, and after that we will decrease the row, and that becomes less than 0. So answer will be 2. Now if single columns are there, for example our grid is this. For better visualization, this is our grid, only single column is there. So we will start with the bottom left, and because it is negative, it is negative, so we will increase the row, we will decrease the row, and by decreasing the row we will go to the next one, again we will decrease the row, and because it is positive then we will move to the right. We increase the column, and column then exceeds the total number of columns, so it stops. So in both the cases the n minus column value was 1, so 1 plus 1 was again 2, so 2 will be output. So our algorithm handles all of these. So now we can submit the code having checked these boundary cases. Let's submit it. So all the test cases passes. The code passes because it correctly uses the sorted property. It counts groups of negatives instead of checking every element. It runs in order m plus n time. It uses order 1 extra space. So what we have learned. The main learning is when a matrix is sorted, we should not always use brute force. Here the sorted structure helped us skip many elements. We learned the staircase traversal technique. This technique is useful in many matrix problems where rows and columns are sorted. The key idea was start from a corner where you can make a definite decision. In this problem, bottom left works beautifully. If value is negative, count the full right side. If the value is non-negative, move right. Now let's discuss common mistakes. First mistake, treating 0 as negative. Remember 0 is not negative. So the condition must be grid row call less than 0 and not less than equal to 0. Second mistake is adding the wrong count. When we find a negative number at column call, we add n minus col because all elements from current column to the end are negative. Third mistake is moving in the wrong direction. So let me list down the mistakes. So first mistake is treating 0 as negative. And second mistake is adding the wrong count. That we commonly do. These are the mistakes that we commonly do. Third mistake that is commonly done is moving in the wrong direction. If the number is negative, move up. If the number is non-negative, move right. Fourth mistake is forgetting the loop boundary. This is a very, very common mistake. Forgetting the loop boundary. The loop should run while row is greater than equal to 0 and column is less than n. And the fifth mistake is not using the sorted condition. So the point is brute force will pass because constraints are small, but the follow-up expects order m plus n thinking. So that was LeetCode 1351, count negative numbers in a sorted matrix. We started from brute force, understood why it is order m star n, then use the sorted matrix property to build an optimized order m plus n solution. The main takeaway is whenever rows and columns are sorted, think about starting from a smart corner and moving like a staircase. That's it for this problem. See you in the next one.